hi. Just finishing my morning workout. Excuse me for a second. I'm kind of thirsty. Let me get a drink of water. That was good. Have you ever thought, where do we get our water from? I know, I take water for granted, and maybe you also, but what if we were to trace back the water coming from our tap? Where would it lead? Have you ever thought about that? Well, in this video, we're going to explore where our water comes from. We'll ask questions such as, how much water do we have? Is it coming from a surface source, such as from a reservoir, river, or spring? Or is it coming from a groundwater source, such as from an aquifer? Why should we ask or care where our water is coming from? Well, consider for a moment that you don't know the answer to this question. How would you or one be able to effectively manage this precious resource? With that in mind, shall we start? Let's see here. Coming through here. Yeah. Okay, let me go here. We have arrived. Have we found our source of water? Well, speaking of water, excuse me, I'm a little thirsty. That was good. So yes, we have arrived at the City of Lockhart's water treatment plant that's located off of Old McMahon Trail in Lockhart, Texas. Let's see if we can find out what the primary purpose of this water treatment plant is. What kind of water processes are involved? What kind of water quality testing procedures are conducted, how much water is treated, and of course, is this the source of water that we've been looking for, or is it somewhere else? Now let's talk with Eduardo Montaña from Guadalupe Blanco River Authority, who helps manage and operate this plant for the City of Lockhart, to help answer some of these questions.
Have a groundwater source, and we're bringing that water from the Carrizo Wilcox Aquifer. Probably approximately about 7.5 to 8 miles, and we have two different lines that we bring the water in to the water plant. We have a 14-inch and 18-inch line. We treat about 157 million gallons a year, which comes out to about a 0.4 million gallons per day, and that's well water. At our plant, we, like I said, we bring that water from the wells into the water plant, and the first thing we do is we go up through the aerators. Water goes through the aerators so we can get the aeration to gas off the hydrogen sulfide, and then we drop that water into our raw basin and start feeding the water with some chlorine. Chlorine brings the iron out of solution and also begins the disinfection process. Then we go from there, from the aerator, we go to the plant itself. We take it through some filters. Filters are have the media of sand, gravel, and anthracite. That water goes through there, gets filtered out. Then we go to a chlorine basin where we add additional chlorine to assure that we have the proper chlorine residual before it hits the distribution system. At the plant, we run 3 different samples or 3 different tests, mainly chlorine test for chlorine residual, pH, turbidity test, as well as the clarity of the water. We run one off of each filter, and then we also do a bacteriological test.
Well, I heard that the groundwater wells were 8 miles away. Wow. Well, let's continue, shall we? Well, it seems like we've arrived at our destination, our source of water. Or have we really? We have arrived here at one of the City of Lockhart's water wells. A water well is completed basically through an excavation process. In this case, drilling down to access the groundwater. That's right, groundwater right below us. Several years ago, this well that you see here was a replacement well by the City of Lockhart. What were the processes involved in completing and drilling this well? What were the components of this well? Now let's talk with Christian Rivera with Allsay to explain the basic components of drilling a public supply well.
It's like I said, water is an undervalued resource. Is one thing I always say here. A lot of people just think, oh, here we turn the tap on and hey, water comes out. They don't know the process that it goes through. So we'll start with the construction of the well. The gravel pack and the screen, they act like filters to keep sediment back. Then you have the conductor casing, which is cemented in place. This allows to keep aquifers separated or not to expect any undesired water to enter the well. Then from there, you have your pump in the well. The pump is your driver that lifts the water from the well to surface, and it travels through a column pipe. Then it goes through the discharge head, which acts like the 90 that goes into the flow line. And then all of this is driven by a motor, whether it's a submersible or a vertical turbine motor. That's the driver that pushes the water, lifts the water. Many things help in this process in determining the size. For starters, having the knowledge of the water wells in the surrounding areas, knowing the aquifer, the size of other wells, screen slots, and the screen size are used as a guide. The final capacity and the horsepower is determined from the pumping test. The pumping tests provide a pumping level at a desired rate, or GPM, plus the pumping level and the amount above ground head, plus the friction loss, which equal the total dynamic head. And with all of that, you multiply that together, divided by 3960, which is a constant, and equals your brake horsepower. The well screens are very common in unconfined and semi-consolidated aquifers. The screens are used and act as a filter along with the gravel pack to allow the entry of water while holding back formation sand and sediments. Also, the screen helps keep the sediments behind and also acts like a structural support in the aquifer. Yeah, when drilling, the driller's always observing the drill cuttings. One factor when you hit a water-bearing sand is you see sand or gravel that is typically comes with the water, or with the cutting, should I say. Another indication is the drilling mud starts to thin out. Our water losses in our mud testing that we perform may increase because of the water-bearing formation.
Well, we have found the source of water, and we have learned the processes of accessing and treating the groundwater. But this leads us to ask us, how far down is the groundwater? And how much groundwater is down there? Is it replenished? And if so, how fast? Last, I wonder if this groundwater has always been here. These are the questions that we posed for William Fethergale Wilson, a geologist with Plum Creek Conservation District.
No, the groundwater has not always been there, in the Wilcox in particular. This map is a map or contour map of the age of the water in the Wilcox, from the outcrop to the subcrop that goes beneath the Carrizo, which is that stippled yellow line. You can see that there's 10,000 years, 20,000 years, 30,000 years, and 40,000 years. So it's taken the water that fell on the surface 40,000 years to reach the subcrop that where it crops underneath the Carrizo, down at the right-hand side of the slide. So the groundwater is moving very slowly down gradient at about 0.00037 miles per hour. It took 40,000 years for that water to move from where it says 0 at the top, where the outcrop was, and it was still about the same place that it was 40,000 years ago until it got 15 miles down dip. So no, the groundwater has not always been there. That's including the water that is in the brackish and the saline water that is within the Edwards as well. The Edwards is by far the largest aquifer we have in the Plum Creek District. And there's a total amount of about 10.194 billion gallons of water, most of which is in the Edwards. The Edwards is not presently accessible because it's brackish or saline, but the water, say, in the Wilcox is about 2.7 billion gallons. But if you take 30% of the overall amount of water that will finally be recoverable, including the Edwards, you have about 3 billion gallons of water left that we could produce in both the Leona, Carrizo, Wilcox, Edwards, and some other smaller aquifers. If you look at this, the fresh water is classified as 0 to 1,000 parts milligrams per liter, while brackish is 1,000 to 10,000 milligrams per liter. Saline is over 10,000 milligrams per liter. The Edwards right now is only accessible because of the presence of the Edwards Aquifer Authority to the east of Highway 183. There are 3 primary aquifers and 1 future aquifer. And then there's some others that are very small, which are alluvial beds, and number 6, other, are very shallow sands, things of that nature. Now, the Leona is an aquifer, and it is used for mostly watering lawns because of the pollution problem that it has now with nitrates. The Carrizo is also a large aquifer, but we don't cover the Carrizo. The district doesn't cover much of the Carrizo. The Wilcox is our largest aquifer, freshwater aquifer at the moment in time and space. And the Edwards is the largest future aquifer for the district. The Wilcox itself is the largest freshwater aquifer we have in the district. And it has 3 members. Wilcox had 3 members. The Calvert Bluff is the lowermost member of the Wilcox. And it moves essentially from the top of the map there and where it says Lockhart. But it actually it's located where it's eroded off the first part of the section that's painted brown, and it moves to the southeast. The arrow points to an erosional channel that is very significant within the county and within the district. That's called the Yoakum Channel. It cuts out completely that aquifer, and there's nothing but a shale, thick shale section left in that fill deposit that was a very big canyon at one time. Now the next slide which is the middle member of the Wilcox, exactly the same situation. And that's the thickness of it, from 0 to 400 feet thick. And it moves again to the southeast and is largely cut out by the Yoakum Channel. The third slide, going to now, is actually the lowermost portion of the Wilcox. It's over 1,000 feet thick down in the southeast corner of the county, and it moves from the outcrop to the southeast once again and is partially cut out by the Yoakum Channel that's over 1,000 feet thick over to the east. So those are the three members of the Wilcox, and they're all moving water at a very, very slow pace. And it takes 40,000 years to get to the base of the where the outcrop is in the brown section, which is an extremely slow movement to the southeast. I mentioned the Yoakum Channel that cuts out a large part of the Wilcox in the eastern part of the county. The Wilcox is a submarine or subaerial canyon that developed similar to this canyon during the portion of the middle Wilcox all the way through the upper Wilcox and a portion of the lower Wilcox as it goes further down dip. On a cross section across it, it looks like this. There's 1,200 meters of shale deposited now in that canyon. The canyon goes all the way from the outcrop all the way down to the Deepwater Gulf of Mexico. And at the time, the Deepwater Gulf of Mexico was an inland sea of very small magnitude compared to what it is now. You can see where the dotted line is. That was the inland sea of the Gulf of Mexico. And it was a canyon that moved down from Caldwell County all the way down into the inland sea at the time of deposition. And it was a very large canyon. It's not the only canyon, but it is a canyon that did run through the county and did limit what the Wilcox is able to give up in our district and within the county of Caldwell. Thank you.
Well, there you have it. We have traced some of the water sources of the Plum Creek Conservation District and learned the basics of how it arrives at your tap. Join us next time as we take a more in-depth look at the aquifers of Plum Creek Conservation District. Until then, please see the discussion guide questions that you will find at the bottom of this page. So long for now.